As you mentioned, my name is Jonathan Bailey, and we'll be presenting on the ACEC stormwater pump station. It's too tall. Okay. So just quick overview. I'm going to be going over the history that brought about the project and go quick project overview and design, along with physical modeling, pump testing, construction, and then key takeaways. Okay. So a picture you can see downtown Dallas and Trinity flooded. This is during construction, but history is Dallas has been known for floods for at least 100 years. And Dallas floodway is approximately 6,100 square miles. And there you can see the watershed area below. But just a little timeline going through of all the major floods and bonding programs going through, and then when levee was constructed. And then for our current project, it's going to be over here closer to after 2010, when finished design and going to construction. So that's how it currently looks now with the Dallas floodway. Okay, so this is the Dallas storm drainage system. What you have here is City of Dallas limits, and then all the red is basically their stormwater pipe network. And then all the floodplain area is going to be in blue from their lakes, and then the above the 100-year floodplain levels. So Dallas is comprised of 661 miles of creeks, almost 2,000 miles of stormwater piping, 14 detention basins, 11 sump areas, and then 17 stormwater pump station, which includes the new Trinity Portland that's being designed and constructed now, and then 30 miles of levee, and then 39,000 acres of floodplain. Here's another overview for the interior drainage system of Dallas. So project right now we're talking about is Able, which is located in this, looks like a small area, but does receive a lot of flow. So altogether, as kind of mentioned before, is you got the gravity storm system. You have 6 pressure sewers in this, 8 pump station sites, 7 total, sorry. And then the levee system, as we mentioned earlier, is the 30 miles of it. Okay, now focusing on the Able drainage system, which is located over here. So basically, this is going to be just south of downtown, and it brings it in a little closer at the bottom image. And there's basically 3 square miles contributing to this, and then 9 sub drainage areas. And you can see the 9 listed there, and that all goes into the Able sump that this stormwater pump station was built. As you can see, the majority of this is area 1. That's where the majority of the flow is going to be coming into the Able, while these other ones contribute, but not near as much as area 1. So altogether, they call this Sump A. There's 9 interconnecting ponds. As you can see them on the bottom right image, you have 1, 2, 3, all the way to 9. Area 1 is going to be majority of the flow going into this pump station. Originally, this pump station was started design in actually 2008. So in 2008, the pump station was further located down here and was eventually moved back to the existing site now, where the original 2 pump stations were Able number 1 and number 2. So this, obviously may design a little longer. And so that's the reason why it's at where it's at today. It's just, that's where the majority of the flow is coming through. So to do that, if you were to go at the previous location, you're going to be moving a lot of flow through under a lot of bridges, and they felt keeping it where it is existing with the previous 2 pump stations was best. Okay, so here's the project overview. Able is the largest stormwater pump station in the city of Dallas. It is one of 3 concrete volute pump stations, Baker and Poplar Hill being the first 2. It's actually the largest concrete volute pump station in the US. And then the facility itself is LEED certified. So the capacity total is 880,000 GPM, which is approximately 1.3 billion gallons per day. There's 4 pumps total, each doing 220,000 gallons per minute at around 57 to 60 TDH. And then we have basically 2 submersibles at 25,000 GPM. This is going to take the majority of your rainwater flow, anything less than a 100-year flood event. So these are the workhorses actually at the station. They're constantly moving flow in and out. Motors used were 4,000 horsepower motors. They're at 715 RPM. They are very large. They're water cooled and induction type. Electrical services, we have dual primary feed from Encore, with actually there's three, there's a third one as a backup if one of these do go out. Full HVAC, and then SCADA from flood control headquarters, which we ran a new fiber all the way from headquarters down to the station. So the original was small able that was constructed in 1932. It had a capacity of 80,000 GPM. And then large able was added in 1953, which had a capacity of 140,000 GPM. So as you can see in the bottom left image, you have small and then large able. And this was the original able pump station site, column number 1, number 2, with able number 3 replacing both of those and bringing that total, as previously mentioned, 880,000 GPM. So new configuration during design, we looked at conventional vertical turbine pumps as well as concrete volute. We looked at many different manufacturers and ultimately was selected with a concrete volute and it was Flowserve. At the time, they were out of the Netherlands, but they were now been sold and now a Spaniard company. So the reason for that pump selections, the large diameter impeller, and there's many things for that. It had to do with the wet well depth, shaft length, and really the main thing is what the city wanted is inspection and maintenance. They can walk, and when the sump's empty, they can walk into it and inspect everything and see, versus if you have a vertical, you have to pull the pump and send someone down. So a picture of it with the contractor looking at the volute being installed. Okay, here's an overall. So you have your pump station on the left. And it's collecting from the sump. This is the main sump area. And then from area 1 comes this direction is the sump, and all other areas feed into the sump from the east. And then the levee, so the pipes had to go, sorry, right here. Pipes had to go up and over the levee. So this side is all pumped, and after the levee's gravity. So pump side is 108-inch diameter pipe, and then gravity side is 114. And then as you continue on the gravity side, you go down to the Stilling Basin, which then ultimately goes to the Trinity River. So with the design, we chose to do physical modeling because you have to, for something this size, you really want to get an aspect of it and see ways of improvement. It's not everything could be seen, obviously, in pen and paper as you're designing items for each part of this pump station. So several physical models was reused during design. Sump and pump intakes, we're looking at that, form suction intakes, pump discharge piping. Discharge structure itself, the Stilling Basin, and this is all performed by Northwest Hydraulics. So you could kind of see their model here is what they used what they made in their lab with the flow recirc going around. So here's the physical model they made. You could see the piping. I forget the exact scale of this, but it was decently sized, as you can see with the background, the top of it. So this was used to model the intake. And so what this showed is we were getting some vortices and flow wasn't equal. So that's when they put some flow vanes. And so as you see them down there in the bottom picture, the flow vanes were added. And then further, they had to make these front parts of the vanes curvature, because if you just had them square, it just wasn't working. So you had to kind of direct flow with the fillets. And then continuing with the model, they modeled the discharge piping. And so the original design was at top. We had just a little air release to kind of let flow go out to the gravity and then out to the Stilling Basin. But then once modeled, found out that we needed to have 2 air releases and then size that accordingly, just obviously for noise constraints as well as getting the flow in there. Because when you were modeling it, I think the next slide is going to cover it a bit. Yeah, so additional air vent helped release when the river stage is above 388. If without that air release, none of the flow was going to get out. So that air release helped contribute to flow and going that way you could discharge to the Trinity during higher levels. And you can see the model there on the image. So the Stilling Basin model, similar. We had our original design, which is on top, which came into a box and flow went up and over the top and out. But after looking with this physical model, it was better to have a wall to hit the structure, bring the flow up, and then have a step discharge to reduce the wall footprint and takes away a lot of the velocity. Okay. So pump testing, this is going to, with the concrete volute pumps, you can't do testing when they're just too large. There's no way, and the size of water volume, there's no way to do it before it gets shipped out to site. So you can test each individual component, like we've done witness testing, the gearbox, the motors, even have people come look at the impeller. I think that was out of China. There's many different components that went together. So once everything is on site and installed, well, that's when we had to do the field testing. Challenges, discharge flows to river outfall. How do you can't just pull from the river and keep going back in. There's not enough water. So what we had to do is use the sump and somehow recycle flow in the sump that's being pumped through it and just keep recirculating that water. So to do that, we ultimately have 2 pipes with the orifice plate to emulate the head on you see on the piping system, and that would shoot water up and just recycle that way. So as is here, the solution, impound water within the sump, recirculate flow, riser pipe with the orifice plate, and then manholes with access so we can get some flow and pressure readings. So we can actually test what the pumps were performing. So here's a little look at that. You have your discharge from your pump, comes out, you have your flow and instrumentation readings here, and then here's the orifice plate where the water's shooting up, and it just goes back to the sump and then gets re-pumped in. So, and then the size, 60-inch diameter, 40-inch diameter orifice, that was the best that we could mimic the head that the system would actually see if it was going all the way up to the top of the levee. So there are those being installed by the contractor inside the sump, and you can see the discharge piping in the background. So what we're looking here, were parameters measured were the flow, pressure, sound, vibration, and then the motor voltage and current, power factor, temperature, and the lubrication system. So we did a 1-hour test for each of the pumps and then 8-hour endurance test. I don't believe all 4 were tested together. I could be wrong, but I know 2 and maybe 3 were. Just the amount of power draw. So with the power draw, the problem with that is when you're doing pump testing, you're bringing 1, 2, 3, however many pumps all online at once, versus during a storm, you would have 1 pump come on, then the next one would kick on. So with this testing, doing 2 at once, it made a huge power draw to start the motors. So we had Encore give a call to the contractor to stop testing, or just because the power draw was so much on the line with the hospital on that grid, same grid. So there was some challenges there. So here's the field testing. As you can see, basically that is a standpipe, and you can see the vena constricta. So that's going to be the water shooting out in the middle. It's a little hard to see, but imagine a hose and you're just having this jet of water coming up. So that's what that's showing. Once I click, there we go. And that's just the video of the pump test. Just showing you that. The one with that pipe is that's a 24-inch aerial crossing. That was part of the project that we had to replace. So field testing results. Orifice plate, could slightly higher back pressure than anticipated, but the pumps did produce about 200,000 GPM at 65 feet ahead, which is close to the design point. And what we did find is the pump efficiency was actually higher than expected or stated. Just some lesson learned here. Just on that straight run of pipe, it wasn't enough to get a good flow measurement reading just because of the short length between. And then overall maximum flow variation was only 3%, and the maximum head variation was 0.5%. So that right there shows some images of the 2 pumps being tested. You can see both flumes coming up. Just some more pictures and with the contractors behind. And there's the overall aerial. So another thing with this project that made it a little difficult is, I think it was mentioned earlier in a technical session by Jack, is so you're testing and you have these pipe, and here's the original old and large able. Part of the specifications or part of the project itself was you cannot decommission small and large able until a portion of the station is online, because you have to have flood prevention for downtown Dallas. So with doing this testing, they tested, I think this is 9 and 10 pumps. So once these were online and testing, when everything went through, you were then able to decommission the original two small and large able. And then after that, you then go through and put the remainder of the piping through. We looked at ways to kind of keep them, kind of rerouting the piping, say a little bit further south of the site and around, but then head differential between the two systems is you couldn't have 4 of the same pumps. It'd be if you had one running on different parts of the curve just because of the more losses and whatnot. So go a little over a bit of the construction on this. It's just going to be a picture overview going through the construction progress. So this is at the beginning. So you get in a lot of the sump dug out and you're starting to get a lot of the, the pump station site excavated. So you're rerouting the sump. You're trying to get it because the original sump, you could see came through this Houston Viaduct and it went this way, right? The original sump is right where our pump station site is. So we had to reroute the sump and then they could start their excavation, get all the shoring in. And a little more picture of the trenching tiebacks, pier supports, and the foundation slab. There is a lot of piers here. You imagine with being in the existing sump, there's a lot of uplift pressure on one with all the concrete. So really, these are a lot of 36-inch diameter piers throughout, a couple of 24s. A little bit of pumps on the building construction. A lot of rebar design that goes into this. So the whole thing is concrete structure, so even with the concrete volute of the pump. So a little bit further in constructing, getting the discharge pipe in. And then right there, you can see the volutes going in. So the volutes are already cast, they come in. And then after there, you then do your building structure around there. And as Jack mentioned previously in the technical session is these pumps are installed. You build the building around the pumps. Pumps go in first. It's not vice versa where you have the building and you drop your can pumps in. So the first part is getting pieces of the pump in and then it's integral to the construction of the actual building. You can see the concrete volute transition piece. So that square piece comes directly off the volute and it transitions it to the circular pipe. And then a little bit more of the construction area with transition pieces in there with the sump in the foreground here and existing large and small able. And so there's a stilling basin construction on the top. This is going to be out there closer to the Trinity. So that's where once that gets done, it's going to be rerouted on the discharge. So now this is located here. That goes straight out to the Trinity. And at the bottom, due to the electrical, that's just conduit coming in. It's just tons of conduit. There's an overview. So this is going further construction. You now have those flow veins from the physical model already in, and then getting some of the building construction going on in the electrical yard, encore yard, and the city of Dallas's transformers. Another view, stilling basin, and then the pump stations in the background. As construction progresses. And then now the building structure starting to get in, starting to get more of the piping going, and you see on the right. Just in stages, it gets pieces inside, interior and exterior. And this the first discharge piping is going in, so 9 and 10 over the levee, and then finished over the top. And this is the building itself, called like a architectural sail, more or less, but it gives it more of the modern look of the building. That's what you see on the outside with the reflective, I believe it's aluminum. Further along is right around pump testing time. So you're going to have your discharge piping fully installed. You're going to have your existing pump station still in service while the building's pretty much the shell is already constructed. And there's that sail I mentioned going through. Interesting enough, a lot of this is channel line glass straight from Germany. Not sure. Special glass that's on there, but it was just part of the architecture of it. Just right during the pump testing, you can see all the risers on both sides. So what the contractor proposed, and it worked out better, is you're able to test both sides of the pump, but test both pumps. You know, you have 9 and 10 was first, and then 8 and 7 went in. But they're able to test the pumps like this without having discharge piping for 8 and 7 go in. So they were able to get those pumps tested sooner that way than having to get the discharge piping in fully on the next piece. A little further along, the sail on the roof totally in. And it's a construction of the 7 and 8 on side, and then the low flow pumps as well. So with these already being accepted by the city, now they can demolish small and large able. So that's what you see there in the excavation or demolition, more like. A little bit further going on, getting close to completion here. And this is going to be on the riverside. So this is articulated block just to help maintain the Corps levee from erosion. And we also have a few structures out here. You have a gate structure on each side. So in the event the pump station ever fails and there is no power, there's 4x8 culverts that can be opened up on each end. That's just the drain. So last scenario, hopefully we'll never have to use that. Just a few more. So there's overall the aerial city Dallas in the background, give you a perspective of the location and the highways going down. I don't know if you could see too much here, but this is all the electrical yard. So he is quite big, especially to service the pumps that are in the station. Some of the finished pictures. Interior of the pump station. And those will be the motors on top. So construction challenges. Always some issues. Obviously, this was done during one of the wettest years that possible, started construction. So this is excavation starting, flooded out, and then here's your pipe pieces in the Trinity River floating down. I think this one's about 2 miles down the Trinity River. So talking 114-inch pipe just floating by. So lessons learned, staging that they were doing it on the riverside. So when the flood came, it did take some of their equipment and a lot of the pieces to build the pump station, mainly pipe, but. And then Jack mentioned previously, you had a crane failure. So the crane's laid out over the top of the station. You could see bending rebar and just bent over the edge there and hits the ground. So luckily this happened, I believe, in the evening hours. So no one was hurt. I don't even know if anyone was on site at the time. So that's one good thing. Then some stuff you can't prevent. So I think the front of the building, we ended up doing a change, or I'm not sure if it was because of this, but it makes it a little easier to clean off graffiti. So some key takeaways and lessons learned. Kind of go over this, but I guess doing design, this project is large and it's spread out 10 years just because of some of the redesign and relocation of the pump station. But you got to look at the whole schedule, scope, budget, just everything you'll learn, especially with reviews, because the Army Corps was involved with reviews at every step of the way. And then there was also some value engineering just due to the size of the project. The client wanted to make sure there was, other ways to get what they want, but also have some cost savings with that. Physical modeling, I highly recommend it for this or any other, not even just large projects, but where you think it could help improve for your client or, your design, because doing that, we found at least 3 ways to make the design better and also cost savings for the client in the long run. Because of, for instance, for flow straightening things, if we would start a pump station and all the flows go into 2 pumps, it's not going to help when you have the other 2 on the side. As you just saw, a large portion of this was in the Dallas floodway. So I believe there's an emergency action plan, but that should be maintained and updated with all the flood events, and keep good day-to-day weather monitoring reports. I think, I can't remember, I believe it was this one where they had to move the crane when they stored it. It was on top, it was flooding, but then the boom was hanging over one of the Houston viaducts. So if that were to happen, that's going to go straight on top of the highway. And this is a large one, contractor versus manufacturer warranty. This project took, I believe, is full 6 years, maybe give or take, for construction. So there was times where the equipment was there on site and it wasn't even installed before the manufacturer warranty was out. So having clear, distinctive when, what the warranty is in there. And then another thing would be when you're looking at substantial completion, especially for this project, we did it in phases where 2 pumps were accepted for beneficial use, and then the other 2 could be finished, but substantial completion for the whole project wasn't until further on. So there's a little bit of, well, is this still under warranty if it was accepted 2 years prior? So just having that stated in there would help a lot, especially getting through construction, trying to figure out change orders to compensate. So this project in 2021 won the ACEC Engineering Excellence Award. So it was featured there, and then the little plaque. And then as well as last year at the ASCE OCA honor. So that's design team in the city of Dallas. They're accepting the award in California. And that's all I have. Any questions? Yes, so the pump itself, yeah, they were all designed there. So obviously we provide, the flow range. We looked at obviously the pump curves. The design was there, and then they used many different ways to construct. So the volute came from China. The motors were, I believe it was Korea. And then the gearbox was out of Lufkin. And then the actual concrete part that encased the volute, that was out here south of us. And then so the flow serve came out each time. They made sure we had inspection of everything. Even in the gearbox and Lufkin, they tested it and made sure everything was working. But the design itself for all those components was from FlowServe. And then we made FlowServe provide everything. We didn't want to have one company provide the motor and we had to deal with that, and FlowServe provided the pump. So with the pump manufacturer, they had to provide all pieces to the pump, including instrumentation and how it's programmed and everything. And that way it's just one source. If anything happens, they have to be the one to fix it.
Sorry. Any other questions, please raise your hand and I will come to you so our friends online can also hear the question.
What was the basis for selecting a 100-year design event?
There's a lot that went into that. Our water resources group did a lot. It was a little more than 100. It's designed for a 100-year flood, but it also lowered the floodplain elevation in certain areas from 4 to 6 feet. So in actuality, you're taking on more water than a true 100-year at the time because you lowered the elevation. But that was also because the way it was is you would have 2 feet of water in some of the hotels if you had a true event. So this is actually designed to make sure it protects that southern part of the downtown area and surrounding areas.
During the pump test, the model test that you did on the pumps, did y'all try to predict about, we got into trying to figure out how high the water column would be when you went through those pump tests, and then we were putting people on each of the bridges during the testing, thinking that we were going to get overspray from the pump test, but it really didn't turn out to be a big issue.
For the water column, no, is that we were hoping not a windy day to keep it straight up and down. But and as we said, it's a little bit higher pressure with the orifice plate. So as you could, I don't know if one of the videos I believe you showed earlier is you can see water shooting out the pipe ends. So it was just a lot of pressure. And those were, we actually added those. That was a addendum to say, hey, let's add some vents because just the pressure and to relieve some of the pumping going to drain. And that actually did help, especially during testing.
During some of the first pump tests, I noticed that the vent pipe coming up near the roof had water discharging out of it because there must have been some blockage or something that triggered the vent pipe to vent, but it also vented water coming down on the the switch gear down below. And we didn't want to have that we wanted to get it covered because we didn't want a water column coming down there and shorting out the circuit and stuff. So that was one thing that was learned.
Yeah, and speaking of the water damage, it reminds me of the inside all the VFDs, water cooled VFDs, and the pipes constantly break. So you're having water filling in everywhere in the electrical.
Yeah, well, I think you just commented on my question. I was gonna ask if these were constant speed or if these pumps had VFDs on them.
They're VFDs. So, yeah. But with that large, the draw starting straight, 4,000 horsepower motors, I would think would be too large, especially for the area and what the electrical feeds can provide.
During this morning's session, they had described some alternatives to soil modification. I wasn't quite clear what they came up with, and it looked like auger cast piles were also considered. And ultimately, what was the foundation consisting of?
I believe it, like you said, the RCAS piles, but what our design is, what we did is our geotechnical sub is we provided the conditions and what we thought was needed, but we allowed almost like not necessarily CSP, but we allowed the contractor to dictate that design because they're going to be ultimately them out there doing their shoring. So the contractor had to submit, or whoever they hired, a sign and sealed of the shoring and how they propose to stabilize the pump station. So we did have the piers on pump station itself, piers, but then the surrounding soils, that's dictated on their design. I forget which firm they hired, but it was a third-party source, and we had quite a few meetings and kickbacks on that just because of what we considered. So I don't
Last question.
think they brought in everything.
The traffic engineer has asked a question. Was there anything historical with the Able, the little Able or the big Able that was saved or anything like historic?
We had to do a historical thing where they looked and said, yeah, it was a kind of a historical site due to the age, but for what was needed, it was okay to demolish because the city does own it. So it's not like it's someone else's, but with that, I think they took the plaque out of there and they kept some of the pump parts, but there wasn't really anything from the site that saved. And they also had to, due to the age of it, I'm sure there was asbestos and they had to take care of that as well.